in oxidation states. Oops. Oxidation states. Anybody know the definition of oxidation state? I'd be surprised if anybody did, because nobody knows the definition of oxidation state. Most people know how to figure out oxidation states because these follow a set of rules. I think they're like 5 steps and 5 or 6 steps in determining oxidation state. How about formal charge? Anybody know the definition of formal charge?
Isn't the number of protons plus the number of electrons?
Kinda, yeah. We don't, that's one way of calculating it, because the number of protons is supposed to be equal to the number of electrons that it has in the neutral atom. And so that's an easy way to remember how to calculate it. But what does it mean? What kind of information does it tell you? Well, in that case, it'd tell you the charge, exactly, the charge. And so what's the difference between formal charge and oxidation state? Are they the same thing? They're related. Did you know they're related? Formal charge and oxidation state. And so are oxidation states the same number as formal charge? No. I assume everybody's done formal charge. Or is that wrong to assume? Well, most people do formal charge to figure out what the best Lewis structure is. And so let's talk about it. Formal charge is discussed later. So versus something called the octet rule. Okay, these 3 methods are for counting electrons and ions or structures. Atoms, or compounds. Come out right, but that's all right. And so when we're counting electrons in ions, you know, there are different ways to count it. And the way of counting this, we look at the bonding, like for example in compounds. If we're dealing with monatomic ions, and there's no big deal. There's pretty much only one way to count the electrons. But when we're looking at polyatomic ions or compounds, then we've got to look. And so this is counting, oxidation state is counting electrons, assuming all bonds, not all, assuming bonding, let's just say, is 100% ionic or tie. Let's just say tie. What does it mean to be 100% ionic? Well, we look at what atom is more electronegative. You guys know the definition of electronegativity? You should know that, right? What is the definition of electronegativity?
Is the ability of an atom to draw an electron or something?
Yeah, the ability of an atom to draw an electron. The stronger the ability, we say the higher the electronegativity. In other words, it's the attraction of this particular atom on an electron. And so winner, you know, here it's winner take all unless it's a tie. You know, winner take all. Whoever's more electronegative takes the electron. That's, you know, what the difference between ionic bonding and covalent bonding. I'm assuming you know this, right? Somebody just give me a quick refresher. What's an ionic bond? What's a covalent bond? Stanley? Or somebody else? Looks like you have it on the tip of your tongue, so that's why. You? No? Somebody else have it on the tip of your tongue? Yeah.
The covalent or shell electrons?
Yeah, good. Covalent bonds, they share electrons. It's not winner take all. It's more sharing. And then ionic is, yeah, transfer, winner take all, basically. Formal charge is assuming bonding is 100% covalent. 100% covalent means, 50-50. No matter what the electronegativity. And so, for example, oxygen is much more electronegative than hydrogen, but they're going to share 50-50, even though we know oxygen has a much stronger attraction for the electron, correct? And so why do we set up something like this? You know why we set up something like this? Remember I was talking about seeing the whole range? This is the whole range here. This is from one extreme to the other extreme. And so this is why we want these numbers, because then with these numbers we see the range of charge. This is, okay, the oxidation state is equal to the apparent charge on the atom. And so if we assume 100% ionic bonds, what is the apparent charge? And so this is the charge on the atom if the bonding were 100% ionic. Now we go to the other extreme, winner take all versus sharing. At the other extreme, this is the apparent charge. And so both oxidation state and formal charge, both of them are charges. It's just giving us a range from one extreme to the other extreme. That's all. And we can't compare them. Can you compare the two numbers? Let's say I had a +2 over here and a +1 over here. Would it make any sense to compare the two numbers? Like say, okay, a +2 is a big charge. Let's say, okay, +2 is a big charge. So let's say that's a big orange, right? And so somebody asks you, what is the biggest orange? They say, oh, I got a +1 apple. Does that make any sense? And so these are apples and oranges. You don't compare apples with oranges. You compare oranges with oranges and apples with apples. So when we're using these numbers, when we get a charge like oxidation state, we only compare it with other oxidation states. Then it makes sense. But it would never make sense to compare it with this, the formal charge. It's the same thing with formal charges. You never compare those with oxidation state. And everybody knows the octet. What's the octet?
Mechanical with more than 8 electrons.
Oh, that's octet rule or something like that. What is an octet, though, in terms of counting electrons? How do we count them? Yeah, total number of valence electrons. You could think of that, something like that. Formal charge and octet, this is later on. But we might as well put things into a context right now. And so oxidation state, we need that now. Let's take a look at the oxidation states of carbon. The oxidation states of carbon vary from +4 through 0 to -4. So oxidation states of carbon. And so at one extreme of carbon, we have +4. At the other extreme of carbon, we have -4. Those are the observed oxidation states. And so why do you think that is? Why do you think it goes from +4 to -4? Oxygen, you know, the ranges for oxygen is? Oh. -2 to plus something. maybe. It'd be pretty hard to get +6 on oxygen, though. Pretty unstable. But can you see where this range comes from? Carbon, at this limit, oxygen would have a -2. Do you know where that comes from? Comes from the periodic table. Take a look at the periodic table and then tell me why carbon varies from -4 to +4. Joshua?
Because it has the ability to either give up its 4 electrons or to take other electrons to fill its valence electron sphere.
Yeah, exactly. That's perfect. Because carbon normally has 4 valence electrons. It could lose all 4 valence electrons, go to +4, or it can gain 4 and fill its octet, fill its valence shell. And so that's why we see that range. All right, +4 is on the kind of on the electron poor end of the spectrum. -4 is more on the electron rich end. Now, rich and poor, this is very qualitative, right? It's not very quantitative. And in order to put this into perspective, like a +4 on carbon is different than a +4 on oxygen. Totally different. You know, a +4 on oxygen behaves way, way different. How do I know? Well, how I know this kind of stuff, because it seems like the range for oxygen should be between -2 and +6. +6. Where did you get +6 from? It gives away all its valence electrons. Do you think oxygen is going to be very happy giving away 6 valence electrons? Terribly unhappy. What about giving, not 6, giving up 4 valence electrons? What if oxygen gives up 4 valence electrons? Is it okay? I think it's got 6. You can lose 4 and still have 2. It should be okay. It should be happy with what it's got, right? It shouldn't be so greedy for electrons. But is it okay? Is it happy at +4? No, oxygen at +4 is terribly unhappy. In fact, if you have a +4 oxygen compound, watch out. You could have an explosion, you know, potential on your hands, right? Well, how do you know this type of stuff? Well, it's not just the numbers, you know. How do I know this kind of stuff? Is not from numbers. You know, the numbers, that comes from the theory. You know, tell me what the periodic table is based on. What theory is the periodic table based on? The theory that the periodic table is based on is quantum mechanics or quantum chemistry or quantum physics. It has to do with, you know, orbitals and shells of electrons and this kind of stuff. It has to do with that. And so we got the theory, we got the periodic table, but does it tell us how violent this stuff can be in certain charges, charged states? You know, because the charge is so important. You know, sodium ions. If somebody says, you know, I'm trying to cut down my sodium intake, are they talking about sodium ions or are they talking about sodium metal? You know, sodium ions versus sodium metal. This is the charge. Sodium metal, which is the nice silver metal, versus sodium ions. Typically on some solid salt or in solution. They're talking about sodium ion because would anybody here consume sodium metal? No, because if you put some sodium metal in your mouth, it's going to catch on fire, basically. Because when sodium metal hits water, it generates hydrogen gas and lots of heat, and the heat ignites the hydrogen gas, so you get a little hydrogen explosion in your mouth. Do you want that? Obviously not. And why? It's because of the charge. You know, electrical charged. And so these, in Chem 4, they called this, do you remember what they called this in Chem 4? Sodium ion versus sodium metal? If you haven't had Chem 4, the book here uses, the textbook uses a now kind of metaphor for it. Anybody remember that? Sodium ion versus sodium metal. They called it Dr. Jekyll and Mr. Hyde, right? Dr. Jekyll and Mr. Hyde. Which one was the stable one? Dr. Jekyll or Mr. Hyde? Which one was the stable? Dr. Jekyll was the stable one. And so which one of these two would be stable? The ion. And so, you know, +1 is a good charge for sodium, whereas 0 is not. Well, how do you know that? You know that because I memorized this kind of stuff. How do you memorize it? Because you've seen it before, right? You've seen how sodium metal might have reacted. I don't know if you've seen it. Have you? Have you seen sodium react? You've seen it. And so this is what we call, you know it from experience. Have you ever heard that? You know, some auto mechanic, they have 30 years of experience. They can tell certain things or something like that. Well, they've just seen a lot of stuff. They've taken a lot of observations, you know. Well, the same thing in science. You've seen a lot of stuff, you take a lot of observations. Because can you do everything? Like, does your auto mechanic all of a sudden pull out and Google, you know, what's this noise, this strange noise in the car? Or do they do this kind of stuff? No. The same thing in science. You know, you're going to have to observe things. You're going to have to memorize things. Otherwise, you know, if you don't have a certain base level of knowledge, you can only make it so far. You know, you have to have a decent base of factual knowledge, because the theory. How well do you know quantum mechanics? You know, in theory, you should be able to predict these things, right? With the theory. How well do you know quantum mechanics that you can use quantum mechanics to predict which one is going to be highly reactive under certain conditions? Do you? Do you know how, you know, the math in quantum mechanics is very complicated. And the mathematics of quantum mechanics have only been used to calculate the exact, you know, answers for one electron species. Anything beyond one electron, you have to use a whole bunch of approximations. And so what we do in laboratory, you know, one of the purposes of laboratory is to gain that experience, right? To learn some factual knowledge about chemistry. And so you might not know that sodium metal reacts violently. You might think it's just like any other metal, but you know, all the alkaline metals, what do they want to do when they react chemically? They want to give up their one valence electron. They got one valence electron, so they give that up. We'll talk much more about this because it's actually a bit more complicated than this. And so, let's see. Yes. Sodium. Oh, that didn't work. surprised. Didn't come up. All right, I have to look for it. I have the link somewhere. But it used to come right up. Anyway, we can see how sodium reacts. In fact, let's just see sodium metal reacting with water. This is the usual demonstration of it. So a beaker of water, a little chunk of sodium placed in here. Sodium has a very low melting point, so it just melts into a molten sphere. It's generating hydrogen gas. The hydrogen gas gets hot enough to auto-ignite. So that's what it would do. Just a little bit of sodium. And so it's totally different than sodium ion, right? Sodium ion is very stable. And so we learn, well, how do we learn about oxidation states? We just put things into perspective. And so let's take a look at carbon, its oxidation states. Some of these. This is sodium and chlorine. Just pause that. All right, there are different ways of assigning oxidation states. You follow a set of rules. So the set of rules is like this. What goes first, carbon or hydrogen? Hydrogen gets what? +1. That means carbon is -4. Because these have to add up. -4, 4 times +1 is +4. That equals the net charge, which is 0. This is the rules that you've used. The rules that we're going to use are a little bit different. We're going to do it based on Lewis structures. And so we take a look at this compound. What is this called? Methane. And then what we do is we assume 100%, what kind of bonding? 100% little pin. Moved there. What happened, if the bonds are ionic, carbon versus hydrogen, who's the winner? Carbon versus hydrogen, who wins? Carbon. So carbon takes those. Takes these, takes these, takes these. And so hydrogen ends up with no electrons. Hydrogen's supposed to have how many electrons? 1. And so it has a deficit. And so we call that +1 for the oxidation state. +1. +1, it's lost an electron, +1. Carbon has 2, 4, 6, 8. It's 8, it's supposed to have 4, so it has 4 extra electrons. 4 extra electrons means -4. And so what we say is, we say that carbon's quite electron rich in this. Electron rich species are what we call reducers, or fuels. Electron poor species are oxidizers. Well, if you think about an oxidizer, what is this called here? What's this molecule called? What? Methane. What's this called? Oxygen. What are the oxidation states of oxygen? It's winner take all. And so winner take all means oxygen versus oxygen. Who wins? Who's stronger? Oxygen versus oxygen. Oxygen's stronger. So this is what results in a tie, right? Obviously, oxygen versus oxygen is going to result in a tie. And so how many electrons does oxygen have? 2, 4, 6. Each line. 6 electrons. It's supposed to have, no, 6 electrons. It's supposed to have 6 electrons, so we end up with 0. 0. Or in other words, 0. This is assigning oxidation states based on structure. This is assigning oxidation states based on the rules in the book. Okay, what does this form? Methane and oxygen produces when you burn methane, what do you form? Oh yeah, a lot of heat, fire, carbon dioxide, and water. And so we're going to form carbon dioxide. And water. Carbon dioxide, even though it's a carbon-based compound, is considered inorganic versus organic. But it's not a big deal. You know, who cares what they classify it as? But technically, it's historically been known as an inorganic. What are the oxidation states in carbon dioxide? We could do it using the formula. We follow the set of rules. What goes first, oxygen or carbon? Oxygen at carbon at +4. I put oxidation states in parentheses, always. Or we could do it based on structure. Oxygen versus carbon, who's the winner? Guess again. Carbon, two times.
I mean,
The same mistake?
oxygen.
Oxygen. Okay. Yeah. Cover your bit. Well, that's good. You stick with it. Stick with carbon. Oxygen is the winner. Who's the most electronegative element on the periodic table? Or what is the most electronegative element?
Is it the one that's closer to fluorine or the one that's further? Is it closer or?
Well, what is electronegativity again? They want to gain an electron, right? And so go to francium, cesium, rubidium, potassium. Do those want to gain an electron? Sodium. Do sodium atoms want to gain an electron? Or do they want to lose an electron? Lose. So it's got to be closer to fluorine. The further you get it from fluorine, the more. In other words, the right side of the periodic table gains electrons, the left side of the periodic table loses electrons. And so oxygen. You know, there are different levels. Okay, remember when I was talking about these? You know, the different levels are people just memorize one simple fact. But there are other people who look at it over and over and see lots of examples of it, and then look for patterns in the periodic table. You know what the definition of metal is? Somebody tell me the definition. What is the definition of a metal? A metal is metals tend to, when they undergo chemical reactions, give away electrons. Yes, that's part of the definition of a metal. They conduct electricity, they're malleable, ductile, good conductors of heat, etc. And so definition of metal is based on properties. And one of the properties is it gives up electrons. This is a chemical property. Physical properties would be like malleable, ductile, that kind of stuff. Anyway, if oxygen wins, it's got 2, 4, 6, 8, which means its oxidation state is, it's supposed to have how many? 6, ends up with -2. This is the same. Carbon ends up with none. It's supposed to have 4, it ends up as +4. Water. Hydrogen versus oxygen. Yep. Electronegativity should be easy. Oxygen. Do you guys know about hydrogen bonding? Hydrogen bonding occurs with the three most electronegative elements on the periodic table. Name them.
Fluorine, oxygen, nitrogen.
Yeah, fluorine, oxygen, nitrogen are the three most. Some people have it memorized. On the Pauling scale, fluorine's a 4.0, then it goes down. 3.5, 3.0. This is what? What's the oxidation state of oxygen? -2. Hydrogen? This is a more detailed structure. You see, in a formula like this, we're missing the structural information. And so this is why we sometimes we don't want to write it in a condensed formula because we lose some information about it. And so we would prefer to do it in terms of the structure itself. And this is not balanced. It'd be pretty easy to balance, but I'm not going to balance it. So we'll just leave it unbalanced. But what I want you to do is get an idea of what the numbers mean. For example, a number of 0 on oxygen means it's happy or not so happy. In other words, compare these two. -2 on oxygen over here, 0 on oxygen over here. Which of these two compounds, or this is an element, which of these two species is more stable? Oxygen or water? What do you think? Oxygen or water? Water? Water is less reactive? Yes, water is less reactive. For example, although it doesn't seem like this, you know, we have oxidation of metals like this. Do you see this? This used to be so, actually this has some sulfur, some green copper. But our tongs, I don't have it. Well, these aren't too bad. Well, they have the clean ones over here. This ring used to be nice, like this, but now it's kind of rusted. You know, it's being attacked by oxygen. And maybe oxygen is not so happy. Whereas if I stored this underwater, you think, oh, if I store it underwater, it's going to corrode. But if it's DI water or distilled water, no, it's not going to corrode. You know, if it's salt water, yes, because the oxygen gets in there and helps attack it. And so this makes me think maybe oxygen with a 0 is what we call electron poor. In fact, the whole origin of the name oxidizer came from what? Oxidizer came from oxygen because oxygen is a great oxidizer. Is it the best oxidizer? No. No, oxygen is not the best oxidizer. Can you think of a better oxidizer than oxygen? Yes. You should be able to think of a better oxidizer than oxygen because you start to apply these things and you start to make connections. Oh, yeah, I remember something about electronegativities and other things. What do you think might be a better oxidizer than oxygen? Fluorine. Fluorine is a heck of, you know, fluorine, oxygen does this. But you know what fluorine does? Fluorine catches this on fire. And so it'd just be going up in flames in fluorine. Because fluorine is a much more powerful oxidizer. Fluorine is very dangerous stuff. Fluorine, they have something called the fluorine chemist handshake. You know, have you ever seen the fluorine chemist handshake? Fluorine chemist handshake is like this. You know. because they lost 2 fingers, you know, and 2 little explosions that happened. They had. And so there are more powerful oxidants. So you get an idea. Yeah, okay, fluorine's even more powerful, but I would say that this is electron poor with these zeros. Whereas a 0 for something like this, diamond. You know diamond? How do you spell diamond? D-A-I? D-I-A. Diamond, you know diamond? Diamond has an oxidation state of 0. And so, does this 0 mean the same as this 0? It's the same number, but it's totally different. And so this is what we have to do a lot of memorization. We have to do a lot of memorization because the theory is just too much work. Unless, you know, you're totally into it. And even if you're totally into it, you make so many approximations that sometimes the answers have a lot of uncertainty in them. And so we memorize certain things. Oh yeah, as far as oxidation state. So for example, methane, is methane really stable, would you say? Like if I filled this room up with methane gas, would you begin to worry that maybe things aren't so stable? Why? Shouldn't methane be stable? Well, as long as there's no oxygen in here, it's probably okay, you know, or fluorine or any kind of oxidizer, it's okay, right? But one thing you notice about methane is what? -4. This is -4 on the light. Well, that's pretty reactive. That must mean this is pretty electron rich. And so we take electron-rich species, react it with electron-poor species, and we get something called a redox reaction. Right? The oxidizer, oxygen takes electrons from the reducer, methane, or the fuel. And so we need fuel and oxidizer to have a redox. Okay, so oxidizer doesn't have to be oxygen. And then we form this. These two are stable. So this tells me +4. What do you think about CO2? Is CO2 fairly unreactive or highly reactive? In other words, is CO2 pretty stable? It's pretty stable. And in fact, people are trying to get rid of CO2 in the atmosphere, right? Greenhouse gas kind of stuff. It's pretty stable. It sticks around, doesn't really decompose. So this says maybe +4 is not bad for carbon, right? In fact, when you look at the pattern, you see lots of +4 carbon. CO2, right? What else? Carbonate. You know, carbonate, CO3 2-. What's the oxidation state in carbonate? Do that as an aside here. Carbonate's pretty stable. Lots of carbonate minerals in the world. What is oxidation state on carbon in carbonate? +4. And so you start to see this pattern. Wow, a lot of +4, and they seem to be pretty stable, so +4 seems to be okay, right? 0 seems to be okay too. I mean, diamond is pretty stable, right? And so the way you have to understand this is the 2-pronged approach. You know what I mean by 2-pronged approach? 2-pronged approach is we can't understand by theory alone. And we can't understand by facts alone because you just don't want to memorize facts, fact after fact. You need a combination. The best combination is a combination of theory and fact. That way we can see certain things, these patterns, hopefully we can understand based on theory. Sometimes the theory we don't understand, so we do patterns and factual knowledge. Maybe that's enough. But the best would be theory and factual knowledge. And this combination, the 2-pronged approach to this will help us understand, because these numbers come from theory, but in order to put them into perspective, we need some kind of factual knowledge too. Otherwise, we can't do it. Can you imagine if you had no idea what these numbers meant? Right? You couldn't put any kind of physical perspective on the numbers. What use are they? Who cares if you can calculate them or not? You know, it doesn't make any difference. And so this is why in science, and you know, the reason I was doing some reading about something over the summer, and I think there's this talk at like, I think there's been a shift away from factual stuff, because I was looking at some elementary school thing, and they were saying, though, we're getting away from memorizing and getting more into. And when I heard that, I thought, wow, you know, that's not right. They got to do some memorizing. Otherwise, they're going to be in trouble later on. Well, anyway, but it's the way you memorize things. You know, maybe some elementary schools just memorize for memorizing. You know, like some people ask me, should I memorize the activity series? Do you guys remember the activity series? The activity series in predicting single replacement reactions? Yeah, every time I've taught Chem 4, I get a number of students, they ask me, because they want to do well, they ask me, should I memorize the activity series? You know, element by element, sodium. Actually, sodium is not a thought, lithium, sodium, etc., right? But I thought, wow, what a waste. You know, that kind of memorization is kind of a waste. Instead of that, do I say do nothing? No, I say, you know, don't memorize. Look for a pattern. Do you see a pattern in it? Do you know the pattern in the activity series? What's at the top of the activity series? The group 1, metals. And so that's easy, group 1. And maybe you can see a pattern within the group 1s. You know, it seems the most reactive are the biggest ones, like potassium, rubidium, and then it becomes less active, sodium, except for lithium's out of place. Do you see that? Lithium's out of place. Lithium is the oddball out because it doesn't fit the pattern. When I look at the pattern for group 1, it's inverted. And so the most reactive are at the bottom of group 1, the least reactive are... Do you see that? That's the type of memorization they should be doing. They shouldn't be memorizing without, you know... And that's the type of memorization you should be doing. And so, remember I was talking about observations? Observations is the first step. And then the next step is looking for what? You do observations and you look for patterns and trends. And so I'll tell you, nobody I know is going to memorize this chart. This chart is a chart we're going to use this semester. When you look at this chart, wow, that's a lot of data. And this chart's actually a lot bigger in your book because it's in Appendix D and it spans like 5 pages. And so most people just look at that and say, forget it. Look at it once, they don't want to look at it again because it's just overwhelming, too much stuff, right? But, you know, what you should be doing is you should be looking for patterns. It's not memorizing line by line, but it's memorizing any kind of trend or pattern that you might see. And in fact, there is a pattern that we see in here. Because this is a chart of oxidizing agents and reducing agents. Oxidizing agents want to do what? Gain electrons. Oxidizers want to take electrons. What's the most powerful oxidizer I talk about right now that will catch steel on fire? Not just steel, but stainless steel on fire. Fluorine. Fluorine is actually at the bottom right of this chart. Fluorine is the most powerful oxidizer on this chart. Is there something even more powerful than fluorine? Yes, there are more powerful things than fluorine, but they aren't on here because they have to comment. What likes to lose electrons? Reducers, like, what are some good reducers? What's quite reactive in losing electrons? Group 1 metals. Where are the group 1 metals? They're all over here. This is called the activity series right here. Lithium, rubidium, potassium, sodium. And so if you look at the group 1, rubidium, potassium, sodium, it's going from the bottom up, except lithium. Lithium's the oddball out here, right? And so you see that activity series. And then some of the less reactive metals, and then some other species are in here. And so we're going to start to look at this and look for patterns and trends, and then we're going to start to try to understand those based on some theoretical stuff, especially oxidation state, because there's something odd here. One thing that's odd is permanganate. If you look at permanganate, what's the charge on permanganate? -1. So, you know, permanganate is -1. It's an anion. And so are anions electron poor or electron rich? Electron poor, electron. You'd think they're electron rich because they're an anion. They got extra electrons, right? And so why? Well, before I talk about that, I forgot. I need to talk more about this. Why don't I just do, this is called combustion. And I can have incomplete combustion. If I have incomplete combustion, rather than forming CO2, I might form carbon monoxide. Or rather than forming carbon monoxide, I could form something called soot, which are just carbon particles. In Chem 4, one of the labs there is you form some soot, and then you try to capture the soot at the bottom of a beaker. Did you guys do that lab?
Which one?
Where you make a yellow flame in the Bunsen burner, and then you hold, I think you hold a evaporating dish above it, and it turns black on the bottom. Yellow flame produces a lot of soot particles from incomplete combustion. Did you guys do that? You did it? Okay. You guys didn't do it? All right. That's a common lab we do here in Chem 4, but why? Because not enough oxygen. You got a yellow flame, it's oxygen starved. If it's oxygen starved, you're not going to combust it completely. That is, take all the electrons from carbon, right? And so what happens is this is incomplete combustion, incomplete combustion. This, if we go all the way to CO2, we call it complete combustion, correct? And so this is a variation of oxidation states here. What if we, hey, I want to go to super complete combustion. I'm going to go to CO3. CO3 possible? Why stop at CO2? Let's go to CO3, CO4. Just dump in the oxygen, more and more oxygen. CO5, CO6, just going to burn the heck out of it. Yeah? CO7, carbon heptaoxide. Then, this is going to completely obliterate my methane. Is that good? This stuff is impossible. Why is carbon heptaoxide impossible? Pretty much. Yeah, what is the oxidation state of carbon here? Well, let's see. This is minus 14 plus 14. And so it should be plus 14. Oh, no, wait. Minus 14 plus 14, yeah. Is that right? How many valence electrons does carbon have? 4. How many core electrons does carbon have? 2. Altogether, carbon has a total of 6 electrons. How can I take 14 electrons from something that has 6 electrons? This is not going to happen. This is impossible. 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 Possible? Impossible. Possible? This is possible, but we have to make sure that carbon loses all of its electrons. And so this is highly unlikely. Probably not possible. Because we'll talk about this later. Ionizing core, valence electrons is one thing, but ionizing core electrons is going to cost you a lot more energy. Core electrons are very unreactive, and that's because they're quite stable. And so this, not with oxygen. And so this is what we call max, and this is what we call the max oxidation state on carbon. Once we lose all the valence, then we have to dig into the core. Sometimes that's possible, so you can make exotic species, which some people like to make. Rather than hit this with oxygen, they'll hit it with fluorine or something even more powerful to try to make something exotic, totally unstable, right? But for us, the normal range, the normal working range is -4 to +4. Okay. And so we have max here. in you know calcium carbide? Let's look at calcium carbide for a second. This is calcium carbide. Is this a molecular, covalent bond or ionic bond? What do you think? Well, it's a metal and a non-metal. It's typically ionic. And so ionic structures, we do like this for the Lewis structures. So we got calcium, which is 2+, and then carbide. Carbide is carbon with 4 extra electrons, 4 minus, it's a complete octet like that, and then calcium ion like this. And then we have this structure, it's going to be calcium, carbide, calcium, carbide. We call this structure what? A lattice. And so this is a solid, it extends out. What do you notice about this? Do you think this is stable like sodium chloride or magnesium chloride or sodium? No, you don't. Why? What makes this unusual in the sense that you should be cautious around calcium carbide? It's the it's the carbon. There are other carbides like used in tools, like silicon carbide, right? But silicon carbide is a very hard material and is used in abrasives and other things for its hardness properties, and it's stable. And so why would something like silicon carbide behave differently than calcium carbide? Well, the reason is because silicon carbide should be more covalent or more ionic. More covalent. Right? And so the bonding is quite a bit different in silicon carbide. There's much more sharing of electrons versus in calcium carbide. And so even though they're both called carbides, the true charge on carbon is quite a bit different in these two. This is much more towards the formal charge end. This is much more towards the oxidation state end. Anyway, but looking at this carbide is going to be quite reactive. It's got a lot of electrons. It's quite electron rich. And so like sodium, sodium is electron rich, sodium metal. Sodium is reactive enough to actually react with water. Right? When sodium reacts with water, it forms hydrogen gas. When calcium carbide reacts with water, I'm not going to balance this, but it reacts with water, it forms acetylene. Acetylene is also called ethine. And ethine has the formula what? Or structure. Well, it's got a triple bond, right? Ethine. What are the oxidation states here? This reaction is a very famous reaction. This is the Miner's lamp reaction. In the old days, you know how they generated light for the miner's headlamp? They didn't have a little battery pack. They had a little bit of calcium carbide. The calcium carbide would drop into the water, generating acetylene. The acetylene they could ignite and generate a flame, which they could use to see. There's a lot of YouTubes on the miner's lamp. You can see it. Generate this. Acetylene. What are the oxidation states on acetylene? No, it's not zero. Is it hard to do hydrogen versus carbon? Who wins? Carbon. Carbon versus carbon. All right, count them. 1, 2, 3, 4, 5. How many is carbon supposed to have? 4. So it ends up with an extra. So it's -1. -1. That's 1. So -1, yeah. It doesn't seem. What's that?
I think you should get 5.
How did I get 5? Count them again. You count 4?
Well, it takes some hydrogen, right?
How many does it take?
1.
How many are in the bond? How many electrons in the bond? How many electrons does that line represent?
2.
This hydrogen carbon bond is a single covalent bond. A single covalent bond has 2, so that's 1, 2, 3, 4, 5. That's how I counted 5.
Since it was a tie, it doesn't take from the other carbon.
No, the other carbon gets the others. There's 6 electrons in the triple bond. That's how I got 5. Well, how does calcium carbide behave? You know, -1 doesn't seem so bad. It seems like, you know, methane, -4 is going to be much more reactive, right? I mean, not calcium carbide, acetylene. So let's take a look at this thing there. I haven't checked. I just saw, I don't know where the proper link for this is, but. Oh, there's another one. There's another one which is just crazy. Have you seen that? This one's not that crazy. I mean, it's still crazy, but. Maybe this is it. That's crazy. It would seem like that. Oh, was that the glow from that explosion? All right. This is not it. I have it on my phone, shoot. Shown that. All right. Anyway, you can see, there's one video that's just, I couldn't believe it was that big. But, huge. And so acetylene, yeah, it seems to be dangerous stuff. It might not be entirely, of course, due to this. You know, there are other factors too. But when this combines with oxygen and heat, you're going to get some trouble. Plus ... And so let's take a look at some of the organic chemicals that we were looking at. Well, I'll have to find those videos, the ones that I have. And so something like ethane, similar. Ethane is going to be electron rich. See the oxidation states on ethane. What do you have here? Can you just do them by sight now? Hydrogens are, the carbons are going to be 2, 4, 6, 7, -3. This one, same, -3. That thing. And so all these hydrocarbons are electron rich, meaning that they're going to be good fuels for oxidizers. In other words, these are good reducers we call them. Okay, if we have ethane, you know, we can partially oxidize it. We don't have to completely oxidize these things. We can use some mild oxidizers, you know, mild oxidizers. We call it O sometimes, but this just stands for oxidizer here. Mild oxidizer. Okay, we mildly oxidize this. In organic chemistry, you have lots of different kinds of reactions you can do. So, and we formed this. This is called what? Ethanol. What are the oxidation states here? Well, it depends. Now, this is it. If you did it like this, C2H6O, do it off the formula. Let's do it off the formula following the rules. The rules say hydrogen first. You can just look up the rules and just follow along. That's +1, then oxygen at -2, and then figure it out. +6 minus 2 is +4, and that means each carbon has to add up to +4 when combined, so each carbon must be +2. Do you see that? That's how we assign it based on our rules. But based on structure, what do you see? Is each carbon +2? No. This is the average oxidation state of carbon. Oops, -2, you're right, -2, not +2. And so that's the average. What is the oxidation state on each carbon? You draw boxes. You draw boxes that helps. This would be quick. 2, 4, 6, 7. -3. Let's draw boxes around here. 2, 4, 5. 5. -1. And so the -2 comes, well, -2 is an average of -3 and -1. These two carbons aren't equivalent. This one's much more electron rich, this one's a lot less. This one's been oxidized. See that? Oxygen is -2. The hydrogens are +1. All of them are the same. +1, +1, +1. If we oxidize this a little bit more, then we form something called a carboxylic acid. This is called ethanoic acid or acetic acid. In other words, nobody ever calls it ethanoic acid. Everybody calls it acetic acid. What are the oxidation states? The two carbons have the same oxidation state? No. Well, let's do acetic acid based on its formula. So this would be C2H1234H4O2. If we do it based on its formula, we get 4 hydrogens at +1, 2 oxygens at -2. So +4 -2, that gives us 0 here. Right? But again, that 0 is the average, so let's do it structurally. And so the left carbon is what? -3. The right carbon? Not -3. +3. You see, those two carbons are going to behave quite differently based on their charge. Remember, charge is everything. Electrical charges is what makes up chemistry. And so these behave quite, this is much more methane-like or ethane-like, right? This one's much more oxidized. Let me ask you this. Will acetic acid burn? Can you burn acetic acid? Is acetic acid flammable? Acetic acid. Yes. Yeah. Do you know your body burns acetic acid? In fact, some people eat vinegar, acetic acid, and actually get some kind of nutritional value from it because acetic acid will have some calories, right? Because acetic acid, what happens? You have some vinegar. Eventually, that stuff is going to be converted into more steps here, into CO2. You exhale out and you get some energy from there. Is acetic acid a great fuel? No, a better fuel would be ethanol. And lots of people consume ethanol. In fact, they consume too much fuel that they get something called the beer belly, right? Which is too many calories, which I have. But anyway, that is some oxidation state. This is some perspective that you can put on this. And so we looked at some alcohols. Let's look at some other alcohols and some other carboxylic acids. And then I need to talk about something else quickly. But some other alcohols, which alcohols have we covered so far? We did methanol, ethanol. Okay, so the next one we're going to do is propanol. Propanol has isomers. What are isomers again? Yeah, same formula, different structure. These are the two isomers of propanol. Maybe there are three. These have the same formula, different structure, and hence they're going to have some different properties. The structures are different. This one is called 2-propanol, or isopropanol, or isopropyl alcohol, or rubbing alcohol. Ethanol, did I say what that's called? It's called ethyl alcohol or grain alcohol. What's this one called? If that's 2-propanol, then this must be 3-propanol? Okay, good. Well, this is called 1-propanol. Or just normal propanol. Oxidation states kind of similar. These are all flammable, highly flammable. These are very hydrocarbon-like. Butanol, even more so. Then let's go to some acids. This is called methanoic acid, or formic acid. Actually, formic acid is a more common name. Formic acid. They say that when you drink methanol, your body oxidizes the methanol. And as your body oxidizes the methanol, it creates formic acid. And formic acid attacks optic nerves irreversibly. And so this is true. This is not some kind of urban legend or anything like that. But if you drink methanol, you can go blind. Do not drink methanol. Right? because the formic acid attacks their optic nerves and you can't reverse the damage. Your body can't reverse that damage. Even worse, it can cause death. You know. Ethanoic acid, acetic acid is okay. People drink that stuff. You know. I saw, you know, at the store, vinegar, potato chips even, popular. But you wouldn't want this, that's for sure. And so, you know, in our own metabolic cycle, we rely heavily on redox reactions. All this stuff about electron-rich, electron-poor is critical to understanding fuel, which is foods, basically. Common oxidizer. All right, so you have to do memorization. So let's talk about the memorization you need to start. Maybe you already have this memorized. And so memorize ions. Let's memorize the ions. Yeah. Okay, so let's start off with monatomic cations are easy. You know, most of them are just the name of the element. We have two types of monatomic cations. The fixed charge. Fixed charge just means they have just one charge. And so we got the group 1, the group 2. Those are all fixed charged. We have actually scandium's fixed charged, but you probably don't need that. What do you think the charge on scandium is?
That's 3.
Yeah, scandium is 3+. Aluminum is fixed charged. What do you think the charge on aluminum is? 3+. So scandium, aluminum. And then there's an elbow in here that you have to memorize. What is that elbow? Oops. My elbow is inverted here. There's an elbow you have to memorize in here. That consists of silver. What is silver's charge? Always. +1. Zinc. Cadmium. 2+. Chem 4, they say nickel is in there, but Chem 1A, Chem 1B, there are too many exceptions in nickel. Nickel +2 by far is the most common, but there are +3 nickel species that aren't that rare, you know. And so nickel we're not going to include in here. And so I'd like you not to include nickel. Chem 4, I know he does that. And then we have the variable charge. The variable charge is pretty much everything else. Now the variable charge is always going to require a Roman numeral in the name. And so this is iron 2, this is iron 3. The Roman numeral is always there, no space between the name and the Roman numeral. Whereas this is silver ion, no Roman numeral here, please. Right? And the same thing with the others. All right, that's monatomic. Now, what about polyatomic cations? Polyatomic cations, we have this one, ammonium. Tell me, is ammonium electron rich or electron poor? You think it's poor because of the positive charge, but take a look at the oxidation states. In ammonium, which goes first, hydrogen or nitrogen? Hydrogen at +1. Nitrogen at +1 times 4 is +4. This is -3. -3 + 4 gives us +1. Electron rich or electron poor? The +1 comes from the hydrogen. So we look at the nitrogen. Is hydrogen +1 unusual? See it in water. But you look at the nitrogen is -3. It tells me that ammonium is electron rich. Ammonium behaves as a fuel, not an oxidizer. Electron rich. And so ammonium ion. What else? Hg2, 2+, what's this called?
That's Mercury 1.
Mercury 1, or sometimes in old literature it's called mercurus. The al's goes to the lower charge. The ich goes to the higher charge. Problem is when there's more than 2 charges, it doesn't quite work so well. Uh-huh.
So do you have to know the older names? Or like,
I mean, mercurus, mercuric, you should, yeah, cuprous, cupric, you should know some of those, but I mean, it's not a big deal. It's not like I'm going to. You should just know it because in the lab, some of them are labeled using the older names. All right, let's go to the anions. Monatomic are easy, right? So, what's this called? Sulfide, nitride. Polyatomics, we have 3 different types. We have the ones that end in "ide." Oops. Monatomics end in "ide." And so if you see the IDE ending, most likely it's monatomic, but there are some polyatomics that end in "ide." What are the polyatomics that end in "ide"? Actually, chloride and fluoride are monatomic, because it's just one. They'd have to have more than one atom. Tell me an anion that has more than one atom but ends in "ide." Okay, I'll just tell you. Cyanide, hydroxide. What else? You know this one? Call.
yeah.
What? What? Huh? I'm sorry? Peroxide. Peroxide. Then you have the ones that end in "ate" and "ite" with a T. The polyatomics that end in "ate." So let's go to the eights. There are 2 types. One we learn by pattern, the other by memorization. This is what they should be teaching the elementary school kids, is to try to figure things out based on patterns and that kind of stuff. But we see a pattern in the periodic table. This has long been recognized. You know what this is called? Okay, what is this called? This is called borate. What's this called? Carbonate, nitrate, fluorate, chlorate. Do you see the pattern? Maybe, maybe not, but look at it more. Okay, what's this called? This is called silicate. Do you see a pattern? Maybe, maybe not, but you should. Okay, that's the pattern. These ones you don't really, it's very easy to memorize. You just memorize two of them. You memorize the two anchors, borate and silicate, and the rest are easy. And then there's 8s that don't fit the pattern. What are they? Like this. What's this? Permanganate. What's this? Chromate. Dichromate. What else do we have? That's it. And then we have the etc. Then we have the per-8s, the per-8s. We have the 8s, we have the ites, and we have the hypo-ites. And so whatever we have as the 8, then this is +1 oxygen, -1 oxygen, -2 oxygen. Same charge, right? All these have the same charge, different number of oxygens. And then, that's pretty much it. Okay, we'll stop here. Well, however you like to do it, flashcards.